What does a diode do? A diode lets current flow in one direction and prevents current to flow in the other. This is the symbol for a simple diode, and there are many different types of diodes, but we stick to the fundamentals for now. If you purchase a diode, you might find it looking something like this. A cylinder with an asymmetrical stripe at the negative side, or the cathode side. The stripe shows us how to put it into the circuit. If we look at the diagram symbol, we can see that there's an arrow and a line. The arrow shows the direction of current from positive to negative. The line is our stripe and looks like a wall that current can't pass through, as well as showing us which side is the cathode. To insert it correctly into our circuit, we put it where the stripe will be connected to the negative side of the battery. To illustrate the function, we can make a comparison to another component, a check valve. The check valve, as with the diode, lets a fluid or gas flow in one direction, but if it tries to go backwards, the valve closes automatically through the pressure and won't let the liquid or gas through. The mechanics are different, but the function is the same with the diode. Alright, now that we know the function, let's talk about current flow. We have two different ways of looking at current. When we are talking conventional flow, we mean that the current goes from positive to negative. This is wrong, but back in the day we believed this was how it worked, and now we have cemented it in all our wiring diagrams and components, and it's virtually impossible to change without huge effort. The actual current goes from negative to positive. This is called electron flow. The short of how a circuit works is that when a material has an excess of free electrons in it and touches another material that has a deficiency in free electrons, or holes, the electrons will be pulled through the positive magnetic field and jump to the positive material. So we can see that current goes from the negative to the positive until both materials have the same amount of electrons, and then our battery is depleted. This is also why you don't have to have a closed circuit to get a current going. You can attach the negative side to a ground or a structure point, because the ground will have more free electrons than the positive side. Whoa, you might say. I know about electrons, but you added a little free in there. What the heck are free electrons? Free electrons are electrons that are held so weakly by the atom that they can move around in the material relatively easily, changing positions with other atoms in the material. We call materials with a lot of free electrons conductors. Conductors have 1 to 3 electrons in their valence shell. Insulators, the opposite of conductors, don't let current flow through it, because the atoms have a strong bond with their electrons, and they have around 5 to 8 in their valence shells. Now, we have something interesting. You might have noticed that I didn't mention either conductors or insulators having 4 electrons. It is because they don't. This is where semiconductors enter the picture. Semis, as I like to call them, no I don't, are materials like silicon here, that has some strange properties with 4 valence electrons. It can act both as an insulator or a conductor, depending on the temperature. This is what we use as a base for our diodes, because with 4 valence electrons it is electrically neutral when it forms a molecule. We will explain this later when we talk about how the diode works. Alright, enough talk about not diodes. Forward and reverse bias. We have 2 terms to describe in which way the diode is inserted in comparison to the direction of the current flow. Forward bias is the direction where the diode lets current through. Reverse bias is when current is blocked by the diode. Let's look at this in practice. In this animation, we can see that in the forward bias, the lamp lights up, because it is in the correct current direction. Now, if we flip the diode, we are now in reverse bias, and the lamp will turn off. Okay, how does the diode work? Let's look at the inside of the diode. We can see 2 materials, P and N respectively. The P stands for positive and N for negative. The balls with smaller balls around them are the white atoms with their electrons in blue. On the P side, we can see that some of the atoms are missing electrons, and on the N side we have an excess of them. However, not every atom on either side has an excess or a hole in them. That is because the material on both sides, if this is a silicon atom, is both made of silicon. We get the difference in electrons through doping the silicon with another material that has either 5 or 3 electrons, like phosphorus that has 5 valence electrons and boron which have 3. We dope the silicon with about 1 boron or phosphorus atom per 1 million silicon atom. And through this we can get a 3000 times increase in conductivity. Since the semiconductor has 4 valence electrons, when we put them together they will share a covalent bond with the other silicon atoms to form 8 valence electrons, which is the maximum for that shell. This means that the strong bonds now formed will not be a good conductor at all. Now why we don't just use conductors directly is because when semiconductors get hot, the resistivity decreases instead of increases, like in conductors. And electronics tend to get quite hot, so less resistivity is good. Let's look at the function up close. So when we put these two dope materials next to each other, so they're touching, we will experience a local current at the contact point, where the closest electrons jump to fill the holes on the p side as far as they can reach with their energy. We call this space of neutral charge the depletion zone or depletion region. It creates a barrier to prevent charge from jumping over to the other side. Unless we have enough pressure, that is, and we call this pressure voltage. Now there is a particular voltage that we need to overcome, and we call that threshold voltage. In a silicon diode, the threshold voltage is around 0.7 volts. When we overcome 0.7 volts, we will decrease the depletion zone until it vanishes due to the pressure of the voltage. And now we have a standard conductor that lets current flow at full force. Now if we flip the battery here to reverse bias, putting positive to the cathode and the negative pole to the anode, the charges will start to pull towards the battery instead of the depletion zone. On the anode side of the diode, the positive charges will gather more closely to the battery's negative pole. And on the cathode side of the diode, it will gather closer to the positive pole of the battery. The result of this, as you can see, is a significant increase of the depletion zone. Let's discuss breakdown voltage. As with most diodes, current will flow in one direction and be blocked in the other. However, if we kept pushing in the reverse bias, turning up the voltage to max, we could force it to conduct in the wrong bias. And we call this breakdown voltage. At the moment of breakdown, the free electrons will have enough energy to jump across the increased depletion zone, due to the high energy electrons bumping into silicon electrons and transferring energy, making them bump into others after that, and so on, creating an avalanche effect that will get current to flow. And so we have current. This will break most diodes, except for a special one called the Zener diode that is actually put in reverse bias in the circuit for its precise breakdown voltage. Because in forward bias, the threshold voltage is a quite flat curve for when it starts to conduct. But the breakdown is at a precise number of volts and will conduct at full force very quickly. Some Zener can be 2.4 volts, while other can be at 200 volts. Now you know the basics of diodes and semiconductors. If you found this video informative, remember to brush your teeth daily. Mouth hygiene is important.